So it's on now?
Yeah.
Okay. All right, so the first topic today is unitary operators. These are very important in quantum mechanics. A unitary operator is one whose adjoint is its inverse. It turns out that any operator that takes us from one orthonormal basis to another is automatically unitary. So this would be a unitary operator. So that's important to keep in mind, and that's one reason why unitary operators are so important in quantum mechanics, because we have different bases or bases that we use to describe physics in quantum mechanics. For example, we can describe physics in terms of position eigenstates or momentum eigenstates. The relation between them is a unitary transformation. It's actually a Fourier transformation. So in that case, the sum is actually an integral. Let's see why this operator is unitary as long as the sum over k is over two sets of complete orthonormal states. In other words, two bases. And the reason is that if you have u dagger, what you have here is alpha k, k, and then this summed over k, of course. Here we're summing over L, and u adjoint means that we have L, alpha L. Remember Dirac's rule for the adjoint of an operator is you just flip the bra into a ket and the ket into a bra. Now these are part of a basis, so they're orthonormal, and so this is a sum just on k of alpha k, and of course that's the identity. Similarly, u dagger u is the sum of these terms, L, alpha L, summed on k, alpha k, k. These are orthonormal vectors, so that gives you delta KL, and we have then a sum k, which also is the identity operator. So this operator satisfies the two conditions for being a unitary operator. Of course, what I've assumed here is that the outer product of any set of orthonormal basis vector, any complete orthonormal set of vectors, gives you the identity operator for that state. And we can think of this identity operator as a sum alpha k, but you can also think of alpha k as a sum u on the state k and k u dagger. This sum over k here is the identity operator, so this is u dagger, and that's 1. So what's important to keep in mind is that every unitary operator maps every orthonormal basis into another orthonormal basis. And so they're very important in quantum mechanics. And one of the reasons why they're important is that inner products don't change. So if we have, let us say, G prime is UG and K prime is UK, then G prime K prime, which is G U dagger U K, is equal to G identity, that's a G, identity K, and that is whatever GK happens to be. So when you change from one basis to another, inner products don't change. And of course, inner products, the important thing is quantum mechanics, because the absolute value of an inner product squared is a probability, or an element of probability. Remember, if you ask questions, you get candy, so. Unitary matrices have unimodular determinants. That is to say, the absolute value of the determinant of a unitary matrix is equal to 1. The reason for that is that 1 is certainly equal to the determinant of the identity. So the determinant of the identity is also the determinant of U dagger U for any unitary operator U. But as we'll learn later this afternoon, or as you learned in college or high school, the determinant of the product of two matrices is the product of the determinants. So this is determinant U dagger, determinant U. This thing is the complex conjugate of the determinant of U transpose times determinant of U. The determinant of the transpose of a matrix is the same thing as the determinant of the matrix. And so this is the determinant of U, complex conjugate, times the determinant of U. And that, of course, is the absolute value of the determinant of U squared. So that's equal to 1, which means, of course, the determinant of U. The absolute value of the determinant of U has to be 1. A real unitary matrix is an orthogonal matrix. So something that is real and unitary is an orthogonal matrix. And we usually use O for orthogonal matrices. And it then satisfies the rules O transpose is O transpose O is equal to the identity. By the way, in group theory, groups of matrices that are unitary or orthogonal are two of the principal classes of groups that have two of the main classes of groups that constitute group theory. They were analyzed by oh gosh, I forget his name. Anyway, he talked about them as the groups of n by n unitary matrices, the groups, and that was called, he called those the groups SU and S for determinant 1. So the absolute value of the determinant of a unitary matrix is always 1, but some unitary matrices have determinant 1, and they form a group. Also, the orthogonal matrices form a group, and those with determinant 1 form a group. And the person who analyzed these first at the beginning of the last century distinguished between SON and SON plus 1. That it turns out that the ones of even and odd dimension are somewhat different. Okay, Hilbert space. The difference basically is that in Hilbert space, you have integrals or infinite sums as opposed to finite sums as when dealing with matrices, finite dimensional matrices. And one thing, again invented by Dirac, is Dirac's delta function. And of course, the first thing you learn about Dirac's delta function is that it's not a function, it's actually a functional. So Dirac's delta function, delta sub x prime, for example, maps a function f into the value of the function at the point x prime. And physicists write this as an integral, let us say, dy f of y delta of y minus x prime. Or I should have written it as delta x, f of x, delta x minus. I don't know why I switched to y, that was just silly. But that's Dirac's delta function. And in fact, for the position the eigenstates of position in one dimension, we say that these are given by a delta function of x minus x prime. Also, for the eigenstates of momentum, we say this is delta of p minus p prime. Examples of operators in this Hilbert space would be a translation operator, u of a, which we could write as a plus x, x dx, and in fact this actually is equal to e to the minus pa over h bar, where of course h bar is Planck's constant divided by 2 pi. So one of the key things about quantum mechanics is that momentum operators generate rotations. This exponential then is unitary because this is I and these guys are all real. A rotation operator, again in 2 dimensions. Here I was in 1 dimension for simplicity. If you want to go to 3 dimensions, of course, all you have to do is draw arrows over these. And then you have p dot a, like that. And when you have here things in 3 dimensions, then these are 3-dimensional delta functions. Rotation operator, let us just stay in 2 dimensions to make things simple. Cosine theta minus y sine theta, x sine theta plus y cosine theta, x, y, dx, dy. So that's the rotation operator in 2 dimensions, and this would actually be e to the minus I theta times LZ actually, divided by h bar. And so equals, and if I write it in, this is xpy minus y px. So that's another way of writing it. So these are examples of unitary operators. They're in Hilbert space, and basically the rule, the way most physicists think about Hilbert space is it's just matrix algebra, which is why I started the course with linear algebra. It's just matrix algebra, but you've got to you need infinite sums or integrals, and infinite sums and integrals are like finite sums. The only thing you have to do is you just need to apply common sense and realize that not all infinite sums converge, not all integrals converge, so you have to be careful occasionally. All right, now, questions? As I said, normally we're talking about linear operators. In fact, everything I said so far this year was about linear operators, and we usually talk about unitary operators. But there is another class of operators. In fact, Wigner, back, I don't know, probably back in the 1950s, middle of the last century, somewhere there, he proved a theorem to the effect that every symmetry is represented in quantum mechanics, either, or quantum field theory, either by a linear unitary operator or by an antilinear anti-unitary operator. And by symmetry, he meant any map from psi to psi prime, and let us say phi to phi prime, such that the absolute value of phi prime to psi prime squared is equal to, well, you don't really need to square it, but the natural thing is to square it. So in other words, that the probability of an overlap of a state known to be psi is found also to be phi, or a particle or a system in the state psi prime is found to be in the state phi prime, that these two probabilities are equal. That's a symmetry. The symmetry is the map that takes you from one set of states to another set of states. And let me just close the thing on phi. The difference between phi and psi is that it's open. So what is an antilinear, anti-unitary operator? Well, k on z psi plus w phi is equal to z k on psi. Whoops, complex conjugate. W complex conjugate k on psi. So this is antilinear. Anti-unitary means that let me just use Dirac notation. I think fooling around with the other notation is kind of silly. Is that this, instead of being equal to phi psi, is actually equal to the complex conjugate of phi psi. So if you had a unitary operator, then you would have u phi, u psi would be equal to phi psi. This is unitary. This is anti-unitary. This is anti-linear. And linear would be, for example, u on c phi plus w psi would be just z u on phi plus w u on psi. So, in fact, let me rewrite these two things just in ordinary Dirac notation. It would be u on z phi plus w psi. Of course, linear means u phi plus w z psi. Where's the z? Oh, sorry, that was a mistake. Let me get my eraser. And antilinear is k on z phi plus w psi is z star k phi plus w star k psi. think I interchange phi and psi. But anyway, I think the rules that I wrote them. So, now anti-unitary operators, as far as I know, occur only when one is talking about time reversal. And I frankly have always found antilinear, anti-unitary operators to be kind of spooky. And I just want you to know Vigness theorem, the reason that it exists, and what anti-unitary and antilinear mean, and we're not going to fool with them very much. I forgot to say what the adjoint of an antilinear operator is, and it's defined in this way. K dagger phi psi is defined as phi k psi complex conjugate. And the result is, the reason for that is that then k dagger phi, what do I want to say here? K dagger k, k dagger k phi psi, and I don't want that, I want just that. K dagger k phi psi is then k phi k psi complex conjugate. On the other hand, k phi k psi is this thing complex conjugated. So this is phi psi star star, which is to say phi psi itself. That means that this is just equal to the identity. So the adjoint of an antilinear, anti-unitary operator is defined so that we have this relation that's characteristic of unitary operators as well. All right, determinants. You guys all learned about determinants in high school and college, or at least in college? Okay. So I'm going to try to go through this long section quickly then. But I'll emphasize the things that maybe they didn't emphasize in your undergraduate math course. For example, suppose we have well, first of all, let me define something. Epsilon ij, this is pass, totally antisymmetric, but of course, since there are only two indices, the totally is redundant, so it's just antisymmetric. Epsilon 1, 2 is equal to 1. Epsilon 2, 1 is equal to minus 1. Epsilon 1, 1 is 0, which is the same thing as epsilon 2, 2, because it's antisymmetric. This is the two-dimensional Levi-Civitas symbol, if you want. And when I say epsilon 1, 2 is equal to 1, there are, of course, two conventions. The other convention is epsilon 1, 2 is minus 1, epsilon 2, 1 is 1. Anyway. So, the determinant of a 2x2 matrix is the sum I equals 1 to 2, j equals 1 to 2, epsilon ij a I1 a j2, and it's also the same sum epsilon ij a1i a2j. This shows you that you can, this I think shows you that the transpose of a determinant, so this is the determinant of the transpose of a matrix, same thing as the determinant of the matrix. One thing that I will mention is that the area of, if you have two vectors, the area of the parallelogram is the absolute value of the 2 by 2 determinant, which is V1, V2, W1, W2. So that's one use of determinants. There are many uses of determinants. The remarkable thing is that determinants are totally antisymmetric, and antisymmetry, there's something magical about it. And in fact, this whole field, the whole formalism of forms that fancy mathematicians use a lot, that's really almost entirely a collection of consequences of antisymmetry. So if we have three, we go to 3 dimensions, we have this symbol epsilon ijk. Now this one is totally antisymmetric. And epsilon 1, 2, 3 is equal to 1. And so, because it's totally antisymmetric, epsilon 2, 1, 3 is minus 1. Epsilon 1, 3, 2 is minus 1. And I don't know, I listed all the possible combinations in 2 equations in the book. The determinant of a 3 by 3 matrix can be written as a sum on ijk from 1 to 3 of epsilon ijk, a I1, a J2, a K3, and you can also do it the same way, but have 1I, 2J, 3K. So I'm going to skip the minor and cofactor thing. It's in the book, and you've got the first chapter. By the way, one can order the book now from Amazon. I think Amazon wants $77 for it. I don't know what the bookstore wants. Volume of a parallelepiped. So if you have 3 vectors, U, V, and W, and let's say U goes this way, V goes that way, and W goes up here, then this thing is a certain, makes a box, and that box is, or the volume of the box is the absolute value of the determinant of U1, U2, U3, V1, V2, V3, W1, W2, W3. And it's also the absolute value of U dot V cross W. Now I see I forgot. Oh, that is the determinant. Okay, it's the absolute value of the determinant is the volume. Now, if you go to n dimensions, Laplace, French mathematician, probably back in the 19th or 18th century. That's funny, I don't give his dates. Anyway, Laplace gave us a formula for the determinant of an n by n matrix, and clearly it's a sum I1, I2, dot, 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 In from 1 to n. And now we use the antisymmetric symbol epsilon I1, I2, In, a I11, a I22, a In, n, or you could have it the other way. You could have this be A1I1, A2I2, ANIN. And once again, you can rewrite this in terms of cofactors and so on and so forth. In other words, the sum AIK, CIK, summed over I or K, but not both. And CIK is -1 to I plus K times the minor IK, and the minor is the determinant of the matrix where you blot it out, row I and column K. And one also has a relation. For example, one could write this, could multiply this just to save time. Epsilon K1, K2, Kn, and then here, instead of 1, I'd have K1, K2, Kn. Anyway, the formulas are already in the book. I emphasize these relations not because you use them every day, but they're occasionally useful, particularly if you're studying group theory. It turns out these relations become relevant. All right, let me just emphasize once again that these things tell us the determinant of a matrix is the same thing as the determinant of the transpose of a matrix. And so the determinant of the adjoint of a matrix is just the complex conjugate of the determinant of the matrix. Now, there's so much antisymmetry in a determinant that if any two rows or columns are the same, the determinant vanishes. And the reason for this is that the determinant, you guys all know that, the determinant of any, that's something you remember from college? That if two vectors are linearly, if the columns are linearly dependent, the determinant vanishes. You had that or you didn't have it? Some of you didn't have it? All right, if some of you didn't have it, let's think about it. First of all, suppose you add, let's do the term, all right, so let me do this EI1 blah, blah, blah. AI11 plus A plus X, arbitrary number, I12, AI22, AINN. So this is a determinant where you've taken the second column, multiplied it by X, and added it to the first column. This extra thing makes no difference. And the reason it makes no difference is that the term that is an E out here and A I1, 2, A I2, 2, dot, 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 I1, I2, dot, dot, dot. This one, suppose you had an I1 equal to 6 and I2 equal to 7. You have 6, 7. So that might be 1. But then, when I1 is 7 and I2 is 6, these are the same, but this thing differs by a minus sign, so they cancel exactly. So the change due to X is 0. One way of writing that is the derivative of this with respect to X is 0. I wrote it differently in the book. So you can add any multiple of any column to any column, and you don't, any other column, and you don't change the term of the matrix. And remember that I said you take any multiple of one column and you add it to any other column, not to itself, but to any other column. And the same thing with rows. And what that means then is that if the columns or rows are linearly dependent, then the whole determinant has to vanish. And that's because you could send AIL into AIL plus a sum YK AIK. So here we're adding to column L a various multiples of any other column. And that doesn't change the matrix at all. And so what one can arrange then is that the first column then is just YK AIK. And if the columns are linearly dependent, then you can find YK such that this vanishes. But that means that you've made one of the columns vanish. And if one of the columns vanishes, the determinant certainly vanishes. And so the determinant of any matrix whose columns are linearly dependent vanishes, and the same thing for any determinant of any matrix whose rows are linearly dependent vanishes. Now let's go back for a moment to this expression, namely that the determinant of a matrix is a sum AIK, CIK, or a sum AKI, CKI. And sum over I or K, either one works. And what you can show is that delta KL, which is 1 if K is equal to L, 0 otherwise, that times the determinant of A is equal to the sum AIK CIL. Okay. Now, if L is equal to K, this is just the formula for the determinant again. But if L is not equal to K, these are the cofactors for, these are the IL cofactors. And so column L has been removed, but column K is still there. Column K is over here also. So this would be the determinant of a matrix with 2 column Ks and no column L. That would be 0. That's why when L is not equal to K, you get 0. This formula, though, tells us what the inverse of a determinant is. And namely, if you divide both sides by the determinant, we have delta KL is equal to a sum AIK. In fact, let me use it with, yeah, right, CIL over determinant of A. So that means that the inverse matrix, A inverse IL is CIL over determinant of A. And somehow I screwed, yes, this is the transpose. So this is, it's really Li. Because if this were, well, this would, what this thing is saying here is, if we write this as in matrix notation, this is I is equal to A transpose C over determinant of A. And so if we take the transpose of both sides, what we get is C transpose A over, let me just write that as, that's another form for determinant. So the inverse of a matrix is the transpose of the matrix of cofactors divided by the determinant of the matrix. And so in particular, if A is equal to A, B, C, D, A inverse is equal to 1 over the determinant, which is AD minus BC, times the transpose of the matrix of cofactors. Well, one can compute that and one finds D minus B minus C A. Of course, these days we don't really have to be aces forming inverses of matrices. MATLAB, which you all have access to, the UNM students, you can invert any matrix like that using MATLAB commands. I'm sure you learned this in high school or college that the determinant of AB is determinant of A times determinant of B. That's something you guys learned in college, right? Okay. So I'll skip the proof of that. It's in the book there. If we look at this formula here, what we can say is that we look right at this way. Determinant of A is equal to C transpose A then one way of thinking, we can derive from that the partial derivative of the determinant of A with respect to a particular matrix element is CIK. And so there's a formula that is useful every now and then, and it's the derivative of the logarithm of the determinant of A with respect to anything is 1 over the determinant of A sum, and it's partial of a given matrix element with respect to this beta, say, whatever that might be, partial of the determinant with respect to AIK, that is CIK over determinant of A, partial AIK partial beta. This is A inverse, but KI, not IK, partial AIK partial beta, and now we're summing over both I and K. But that's the same thing as the trace of A inverse partial A partial beta. Okay. So the bottom line then is, and this is a good relation to understand, the partial derivative of the logarithm of the determinant of a matrix is the trace of the inverse of the matrix times the partial derivative of a matrix with respect to whatever the variable is, say beta. That's an important relation. I didn't learn that in college, and I was a first-year graduate student, and one of the professors rattled that off as though it was common in fact as that the sky is sometimes blue. So I had to think a lot about it. Anyway, but I thought I'd show you what it is. All right, let's maybe I should just say one word about Well, in MATLAB, if you define a matrix, in fact, that's the harder part of MATLAB, is defining the matrix. You guys all know how to use MATLAB, or you do, but maybe others don't?
Right, you can sort of use it.
All right. So suppose you wanted to, let's do a 2 by 2. If you just say A equals that, MATLAB comes back at you and writes 1, 2, 3, 4. Or it may write it like this. You can then say D equals determinant of A. And MATLAB will tell you D equals whatever it is, 4 minus 6 minus 2. You might say AI equals A, and I wrote it this way, but actually what you would do would be say hat minus 1. That's what you type in, and it would give you A inverse equals whatever. It would compute it for you. There's another thing called the permanent. The permanent is like the determinant, except there are no minus signs. That is to say, instead of the epsilon symbol that's totally antisymmetric, you just have the number 1. Jacobians. Any questions? There hasn't been a question in a while. Okay. Suppose we have two systems of coordinates, x1, x2, and say y1, y2. And let's just imagine for simplicity that we can write the x's in terms of the y's and the y's in terms of the x's. And suppose x1 hat and x2 hat are unit vectors in the x1 and x2 directions. Then if we change y1 and y2 by dy1 and dy2, the change in the vector y1, and I wrote it this way, is going to be partial x2, partial y1, x1 hat, plus partial, wait, this is x1, partial x2, partial y1, x2 hat, times dy1, and dy for change of y2, this would move by partial x1, partial y2, x1 hat, plus partial x2, partial y2, x2 hat, dy2. And the area of this would be the determinant. So the area of dy1, dy2 would be then the absolute value of the determinant of these two vectors times dy1, dy2. And these are then partial x1, partial y1, partial x2, partial y1, partial x1, partial y2, partial x2, partial y2. And actually I should have put an absolute value here also. So once again, the idea here is that we're moving in the y's, and if we move, we're in the x1, x2 plane, and we move by y1, then we go a little bit in the x1 hat direction and a little bit in the x2 hat direction. The amount we go is the partial of x1 with respect to y1, partial of x2 with respect to y1, and so forth. Okay, so what this thing is, this thing inside here, the determinant here is called the Jacobian, and it's written as J of, sometimes it's written as J of x/y. More commonly, it's written as J of x1, x2, y1, y2, like this. And however you write it, what you mean is this determinant, partial x1, partial y1, partial x2, partial y2. And then the same thing down here, except it's y2. Wait a second, I screwed up. This is y1, and that's y2. Okay, so that's the Jacobian, and the reason why this is one reason why this is useful is that if we're integrating over some region, dx1, dx2, over some region Rx, f of x1, x2, we want to change variables, integrate over some Ry, and we can write this as f of x of y1, y2, f of y of x1, x2, y1, y2. What you put in here is the absolute value of the determinant of the Jacobian. dy1, dy2. So in other words, you integrate over the corresponding region in y space, but you multiply by the Jacobian. Is that a question?
Yeah, what's the O in this situation?
All right, good question.
Thanks.
Good catch. This is math notation, or at least it was math notation. So Fox of y1, y2 is f of x1 of y1, y2, comma, x2 of y1, y2. So in other words, over here you're integrating f of x1, x2 over a certain region. Over here, you're integrating over a region in y space, and you have to go from y space to x space, and it's like that, f of, and x1 and x2 are functions of y1, y2. This is composition, and this is normally written as big F, little o, big X, looks like that. Okay, that's in 2 dimensions. The same thing applies in 3 dimensions or n dimensions, and it's always simply a Jacobian. The next topic is systems of linear equations. And let me see if I can erase some of the board. And because, oh my goodness, this thing is filthy. So systems of linear equations, and I'm sure you learned about this in high school and college. Let me just therefore do it quite briefly. So Suppose we have these equations. K equals 1 to n, aik xk equals yi. And suppose there are n of these, then this equation in matrix notation is ax equals y. If this is non-singular, that is to say, if there's if determinant of A is not equal to 0, then it has an inverse, and in fact we know what the inverse is. It's the transpose of the matrix of cofactors divided by the determinant, and that's why the determinant can't be 0, because you have to divide by it to get the inverse. Then you multiply by the inverse, and you get A inverse AX equals A inverse Y, but this is just X, so the solution is X equals A inverse Y, or Xi equals A inverse YJ. So that's the formula if it's n. So if this is if these are n equations for n unknowns, that is to say there are n y's and n x's, and if A is non-singular, then there's a unique solution, and it's given by this. So this is the nice case. And when in most problems, that's what you're actually dealing with. But there are a couple of other cases. In some cases, the determinant of A, if the determinant of A is equal to 0, then what that means is that the columns or the rows of A, well, columns and the rows of A, but let's just consider the columns. The columns of A are linearly dependent. Okay. And what you can think of is that this matrix multiplication here is basically taking column 1 of A times x1 plus column 2 of A, x2 plus dot 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 plus column n of A, xn equal to the vector y. Well, if these are linearly independent, then the columns are linearly independent, then they're complete, and you can find coefficients x1 to xn that give you y. But if the columns are linearly dependent, then these n vectors span a subspace. So these vectors, they're linearly dependent now, and so they span a subspace of the vector space. So we get a solution if y happens to be in that subspace. If it's not, we don't get a solution. So that's the situation when the determinant of A vanishes. You sometimes have a solution, you sometimes don't have a solution. If A is in the subspace, you have a solution. If A is not in the subspace spanned by the columns of the matrix A, if it's not in that subspace, you don't have a solution. Now, if you do have a solution, the problem is the solution is not unique. That may not be a problem, it may be a blessing. I don't know, depending on what your situation is. But if y lies in the subspace, then because these columns are linearly dependent, you can find vectors such that, say, ai, zi summed over I is 0. So you add z to each of the x's, it doesn't change the left-hand side, so you have another solution. You have infinitely many solutions. So basically, when the determinant of A vanishes, you either have no solutions or infinitely many of them, depending on whether the vector happens to lie in the subspace spanned by the columns. Is this still working? Yeah. All right, so I guess that's that. So that's the basic idea there. Now, The next possibility is suppose that that you have only m i's. That is to say, m less than n. In this case, the problem is underdetermined. And as long as m of the columns are linearly independent, you have a solution. But the solution may not be unique, depending on whether the columns are linearly independent or not. So that's underdetermined. That is to say, you have more variables than you need to get the solution y. To achieve the vector y, you have more x's than you need. You have more x's than y's, or more n is greater than m. The other situation is where you have lots of y's, but you only have n x's. So you don't have enough x's to get y. So no matter what the matrix A is, it spans a subspace of the space Y, and so you can't get every vector there. But what you can do, and this was something that was worked out by Gauss, worked out so very, very many things back in the 18th and 19th centuries, is he said, well, there's a best solution. So suppose Y is a huge space, you're trying to match 20 Y's with only 10 X's. What's the best you can do? And what he did was to define an error, E, as the sum, I equals 1 to m, and now there are lots and lots of m's, of yi minus a sum aikxk, k equals 1 to n, absolute value squared. And now you want to minimize this. Well, the way you minimize something is you find the minimum of that function as a function of the x's. And so you take the derivative, partial e, partial xl, and you set it equal to 0, and that gives you the equation sum on I 2 yi minus this sum aik xk times minus I ai l. And in matrix notation, there's a very simple way of writing that. It's A transpose Y is A transpose A X. Okay. If A is real, then this thing is a non-negative matrix. If it's also positive, then it has an inverse. And then the solution is X is equal to A transpose A, the matrix, the inverse of that matrix, multiplied by A transpose Y. This is effectively this is what's called a pseudo-inverse. So if this were n by n, we just say X is A inverse Y. But instead, we're using Gauss's formula for the best solution. And the best solution is the pseudo-inverse of A times Y. In the case where A is complex and the X's and Y's are complex, the solution is X is equal to A dagger A inverse A dagger Y. And then this is the pseudo-inverse for a complex matrix. Okay. Lagrange multipliers. This is a very important subject, actually, and I'd really like you guys to ask questions as I explain this in the next 3 minutes. And we may have to start again on Thursday. Remember, there's a problem session tomorrow in room 5 at, it's also at 5:30. No, it's at 5 o'clock, right? 5 o'clock. I urge you to go to the problem session because you'll learn more in the course if you go to the problem sessions, I think. And by the way, in the problem sessions you can ask questions about the homework that's due Friday of this week. And in fact, next Wednesday, the next problem session, I'll actually do any of the homework problems that you want me to do. I'll do them on the board during the problem session. So that's how to get the problem. Now, Lagrange multipliers. So, if you have just the function f of x, just say f of x1, xn, then the extrema of this, or among the stationary points, and these stationary points are given by partial f partial xk equal to 0. So you set the gradient equal to 0, and you get the maxima, the minima, and you also get places where there are saddle points that might do that. And in fact, I think those are called points of inflection, and politicians and financial people love to use point of inflection. Of course, they always have a thing wrong. It annoys the hell out of me. But anyway, so that's how one gets maxima and minima for an ordinary function. But what Lagrange pointed out, again in the 18th, early 19th century, probably the 18th actually, was what if we have a constraint that c of x1, x2, xn is equal to 0, and we want the minimum or the maximum of this thing subject to that constraint. In other words, we're not interested in the actual minimum or maximum, the minimum or maximum of the function, but only the ones that occur when c vanishes. So what we do is this. We say we expect the gradient, we want the gradient to vanish in those directions that preserve the constraint. So in other words, if this is a direction that preserves the constraint and the function does that, we want the maximum of the function as it's obeying this constraint. And that means that the derivative of the function, the gradient of the function, should be parallel to the gradient of the constraint. That is to say, we're looking for dx dot grad f equal to 0 for dx's that make dx dot grad c vanish. That is to say, we're looking for places where the gradient of f is parallel to the gradient of c, and where both vanish. And so the formulas we want then are gradient of f is lambda times gradient of c, and we're also satisfying the constraint. So the, and what we do then is we define a new function, f of x and lambda, as f of x minus lambda c of x. All right, we're basically out of time here. And now we look for the minima and maxima of this function. This is a function of n plus 1 variables because it's got the extra variable lambda in it. So the derivative with respect to lambda is c, and we set that equal to 0. The other derivatives are partial L, partial xj is partial f, partial xj minus lambda, partial c, partial xj. We set those equal to 0. And that says that the gradient is parallel to the gradient of c. So you see now, but the gradient of c, you see, is 0 because we've got c equal to 0. So c isn't changing. So we've actually satisfied everything. All right, well, I'll redo the Lagrange multipliers on Thursday because they're a complicated, they're important and they're kind of subtle. Did you have that in college? Some did, some didn't, is that right? Okay. All right, so are you going to turn it on? Is anybody